All right, so last but not least, let's derive the mole balance for the plug flow reactor, PFR. And so, again, let's go to the University of Michigan Equipment Encyclopedia to see how this thing works. So the plug flow reactor is a tubular reactor, and it's a turbulent flow reactor. And you can imagine turbulent flow being like a plug. That's what you see here, the highlighted region. It travels down the length of the reactor. As it does that, reactants are converted into products, and that's what you see in the bottom panel. So how does this work? This is a tubular reactor. Turbulent flow. This is also called plug flow, hence the name plug flow reactor. As the fluid flows down the reactor, reactants are converted to products. So there are three key assumptions for the plug flow reactor. One, the steady state reactor. The second assumption has to do with this plug that transverses down the length of the reactor. So if you imagine that being a turbulent flow, you could stop that plug at any point along the length of the reactor and take the cross-section, the circular cross-section, and the assumption is that that circular cross-section is well mixed. So I take a very small slice out of the length of that reactor, and I'll illustrate that in just a minute. But within that slice, the concentration and the temperature are uniform, all within there. So what we call that is we say perfect mixing. And the radial dimension. The last assumption has to do with this continuous variation of the concentrations, and also if we were looking at a non-isothermal case, of the temperature as we travel down the length of the reactor. So this assumption is that it's continuous. So we have continuous variation the concentration, and I'll say down the length of the reactor. So like the batch reactor, the PFR does not have a constant concentration. So in the CSTR, the concentration was uniform throughout the CSTR. In the batch reactor, it's uniform throughout the batch reactor, but it changes with time. In the PFR, the concentration changes down the length of the reactor. However, at any snapshot in time, you could pick any location along the PFR, and the concentration would be constant at that location. So lots of things to keep track of there. But the key point here is that, like for the batch reactor, the concentration we'll say and temperature, because eventually we'll talk about non-isothermal cases. It's not constant in the PFR. Has some variation. Okay, so that makes it a little challenging to define the system. So we want to take a mole balance, we have to define a system. How are we going to do that? There's two ways really to do that. If we have a reactor, so we have a plug flow reactor, and a lot of times we're going to draw those, they look like this. So we just draw like a cylinder. And so if we have this thing and we know, for example, what the net generation consumption term is. So we know if we have some value for this. In that case, it's easy. So if we know the net generation consumption term for some component over the entire length of the reactor, and we know the inflow and outflow, then we can write, just the general mole balance. So we would say the steady state reactor. And we could solve this thing. If you recall, when we started this lecture, the very first example we said it was a black box reactor. We weren't going to think about what type of reactor it was or any of the specifics, but we knew what the net generation, and actually in that case it was a net consumption term. We knew what that quantity was for some component, so we could go through and solve the balance. So if we knew that for our PFR, then we're set. We can just do the general form of the balance. In general, though, we don't know that term, so we need to solve for it. So in that case, we have to come up with a balance for the PFR. So to do that, let's draw the PFR system again. So we have this cylindrical reactor, and stuff coming in at the beginning, or at the feed, and stuff exiting. And we said that this is the length of the reactor, so we call this Z, the length, and this is concentration. And if we had some reactant or some reaction going on, we would say the reactant concentrations look like this, and the product concentrations look like this. So products and reactants. So what this says is that if the concentration is varying down the length of the reactor, then that is what we need to capture. So to do that, we go back to this theory of the plug flow. So I can take any point along the length of this reactor. So I'm just going to pick this point here. And I can draw out one of these circular cross sections. So that's a plug. That's a volume element. And that is how I'm going to define my system. So the system it's a volume element, and we're going to say it's infinitesimally small. I know that's not the way it's drawn here, but that's what it's meant to be. So it's infinitesimally small. So in other words, we'll get to that in just a second. And I don't know that I spelled infinitesimally correctly. So the way I will denote this, the length, we can take the length of the reactor. When we talk about a PFR, we're talking about the concentration variation down the length. We can also say as a function of the volume, because really I could multiply the length by the length by the cross-section area and get the volume. So let's write it that way because that's more consistent with the book. So if I do that, when I define this plug, I say that the plug exists at some point V, and then V plus delta V. So this is just some length or volume, and then this is V plus delta V. Delta V is the volume within this plug. So in other words, i.e. which means that is, delta V is approaching 0. So it's very small. So this is how I'm going to write, this is the system I'm going to use. This infinitesimally small volume slice is what I'm going to write my balance on. So I do have inflows and outflows for this. So I have fluid flowing all the way down this reactor. So I have some fluid coming in here and I have fluid exiting. And this is going to be, I can call this F, evaluated at V, and then I don't really have a lot of room here. F evaluated at V plus delta V. And so now I can take my balance. So this is a steady state reactor. So my accumulation term is equal to 0. My inflow is going to be the flow rate of A evaluated at V. So the flow rate, whatever the flow rate of A is right here, that's my inflow. My outflow is FA evaluated at V plus delta V. So my outflow is coming right here. So then my generation and consumption term, that's going to be my rate. And normally I would multiply this by volume. Here I'm going to multiply it by delta V, because the only place where my volume or my rate is valid is in this slice. So my rate is a function of the concentration. The concentration varies down the length of the reactor. So I have to be, at any given point, I have a rate of reaction that's valid. But as soon as I move on, the concentration has changed and hence has the rate. So my rate is only valid in these infinitesimally small volume slices. So this is my mole balance for the PFR. Now, if I look at this, because, I don't think that this particular balance is solvable, but if I look at this, and I remember back to calculus, which for me, I honestly don't. I took calculus 22 years ago. But the Fogler book and other books tell me that this looks like the definition of the derivative. So basically what I can do here to get this into derivative form, differential form, is divide by delta V and take the limit as it goes to 0. So if I do that, I get limit as delta V goes to 0. Yeah, that kind of looks sloppy, so let's just redo it. This right here is what the definition of the derivative is. So that would mean that this term is equal to minus dFA dV. So my balance then becomes equals RA. So again, if component A is a reactant, then RA, the net rate of A, is going to be a rate of consumption, and this is going to be negative. That means that the flow rate of A is going to decrease as we move down the length of the reactor and down the volume of the reactor, and that makes sense because the moles of A are going to decrease because A is a reactant. So here, what I suggest that you do, so we're at the end of the notes, I suggest that you use this mole balance and try to solve the problem that we've been solving throughout. So apply this to the same example, the 2A plus B goes to C reaction, or I don't remember exactly what it is, and see if you can get a solution to that. I think that would be a good practice. And that concludes what I want to tell you about deriving mole balances for common reactors.